Hey everyone, welcome back to another lesson in MCV4U. Today we'll be looking at algebraic vectors in two space, or R2. So here, again, algebraic vectors are vectors that can be plotted on a Cartesian coordinate system. Okay? Again, a position vector is a vector with its head at point P, point xy, and its tail at the origin. It's represented by the vector OP. Again, a Cartesian or displacement vector is defined by its endpoints, and then any Cartesian vector can be translated and worked with as an equivalent position vector. Okay, on the right, what we're going to do is we're going to display the position vector. So again, the origin, we know that is at 0, 0. So that would be our origin or our O. Again, that is its tail. And then it goes to a certain point, okay, which is P, represented by the coordinates x, y, and again, that is the where the head is. So again, remember, again, if we're representing it as vector OP, remember the first letter here represents the tail, and the second letter represents the head. So here again, we're representing vectors in R2 or two space again. Okay, so the collection of all the real numbers in two dimensions known as the R squared or two-dimensional space. Again, the R squared space that is most commonly used is the XY plane. So here R vectors in two space can be represented using X and Y components referred to as component form. So here if we have, again, vector, here we have vector OP, right, as our coordinates, we write that as XY. Again, or here we're writing it in component form, we can write it as vector OP is equal to X and Y. Here it seems that it's one on top of each other. Again, X at the top and then Y at the bottom. Again, so here a position vector with its head at point 3, 4 can be written in component form as vector OP is equal to 3, 4. That would be with the coordinates, or vector OP is equal to 3, 4 written in, again, component form here. So here, if we draw that on our graph on the right, and here it's at point 3, 4. And so here, and that helps us represent, again, our vector here. Okay, so again, uh, vectors in two space, or R squared, can also be represented using scalar multiples of unit vectors along the xy axis. So the vectors I and j, so these unit vectors, vector I and vector j, are defined as unit vectors in the direction of the x and y axis, respectively. Okay, so again, I represents the x-axis, and j will represent the y-axis. So I, again, is the unit vector in the x direction. It has a magnitude of 1, running from the origin to the point 1, 0. Again, here it's either I is equal to 1, 0 in coordinates, or again in the component form here. Okay, again, j is the unit vector in the direction, in the y direction, as magnitude of 1, running from the origin to the point 0 and 1. So again, j is equal to 0, 1 coordinates, or here, shown in component form, 0 and 1. Okay, so here, as we see, you can see that again, j is at coordinate 0 and 1, and I is at 1 and 0, again, starting from the origin. Here, example, a position vector in the component form, vector OP is equal to 3, 4. Again, or again, in component form, vector OP is equal to 3 and 4 can also be written as vector OP is equal to 3i plus 4j, and this form is known as standard basis form. And so here, if we draw this vector on the right, again, what that means here, so if we, again, what that means is we have, okay, 3i plus 4j, and again, it means that there's 3 unit vectors in the x direction, and there's 4 unit vectors in the y direction. So here's how that will look. 3 unit vectors, so 1, 2, 3, and 4 up. So 1, 2, 3, and 4. And that would be our vector here. And again, that's at point 3. Okay, so here again, vector OP represents our position vector, and here represents our vector equation. Okay, so here, continuing on, again, just note a couple of things for notation. Again, if we write CF, that means it's in component form. And if we write it in as SPF, again, that means it's in standard basis form. And again, 1 unit. In standard basis form here. So here it says, write each of the following vectors in the alternative form. Okay, so here, again, we have, again, in coordinate. So again, and we can write it in component form. Again, we're going to go from component form here to standard basis form. Okay, so here, remember the x values are represented by I. So here we have 6i minus, and the y values here represented by j, so minus 5j. Okay, if we look at the second one, here we have vector u is equal to negative 6i plus 3j. And so here we're going from standard basis form to component form. And so here we can write it as vector u is equal to -6 and 3. Here, see, we have, again, vector u is equal to 0 and 8. So here we're going from component form again to standard basis form. And here, again, because here x is 0, so won't have any the I vector, unit vector. And here we'll just have 8, j. Here we have vector OP is equal to -j. Again, we're going from standard basis form to component form. Again, if we look at it in terms of -j, again, it is moving 1 unit down. Okay, so that means that B here, in terms of component form, vector OP is equal. So no I vector here. So it's 0 and down 1, so -1. Okay, continuing on. Again, adding algebraic vectors in here two space. So to determine the sum of two algebraic vectors at their corresponding x and y components. So for example, here we have vector u is equal to ab and vector v is equal to cd. And there's two coordinates. So vector u plus vector v. So again, we're going to add our x components here, which are a plus c. And we're going to add our y components, which are b plus d. So therefore, again, if we want to write it in our standard basis form, so vector u plus vector v will be equal to a c times the unit vector I plus b plus d with the times the vector unit j. If it's u minus v here, so we have a minus c and b minus d. Vector u minus vector v is equal to a minus c multiplied by the unit vector I plus b minus d times the vector unit j. So here, if we're multiplying the algebraic vectors by a scalar in C space or R squared, again, multiply an algebraic vector by a scalar, multiply both the x and y components by the scalar. For example, here again, if we have vector u is equal to ab, then m, which is the scalar, times vector u. So we're going to multiply both, again, the x and y components. So m times a and m times b for the y components. And or for writing as here, as we're writing it as standard basis form. Here, and m times vector u is equal to m a, the unit vector I, plus m times b, the unit vector j. Okay, so the m value represents, again, the scalar, Here, the A times the unit vector I will represent the x-coordinate. And again, M represents the scalar. And here, the B times the unit vector J represent the y coordinate. Okay, so again, next we'll look at the magnitude of the algebraic vectors in 2 space or r squared. And to determine the magnitude of the algebraic vector, we're going to use Pythagorean theorem. So for example, here if we have, again, the unit vector with the point AB, then again, vector u, the magnitude will be equal to a squared plus square root a squared plus b squared. Here, that will be our scalar equation. So let's visualize it and let's draw it on the graph that's provided on the right. So here, again, if we have point A and our point B, here our vector u, again, will be looking at C. So again, which will be equal to square root a squared plus b squared. Again, our point here is at AB. Okay, so let's look at this second example here. So again, if vector A is equal to 2, 4, and vector B is equal to -1 and 3, determine these values here. So again, we can write this in component form. So 2, 4, and -1 and 3. So here we have A plus B. So here we write 2 and 4 plus -1 and 3. So we'll add again what our x components are, and we will add our y components. So here we can write it either as 2 minus 1 and 4 plus 3 again, or we can actually calculate that, which would be 1 and 7. So here it tells us to find the magnitude of A plus B. And so here, again, we know that A plus B is 1 and 7. And so here we see that we know that it is the square root of A squared plus B squared. In this situation, it would be 1 squared plus 7 squared. That's equal to square root 50, which is equal to 5 square root 2. Next, we have finding vector A minus vector B. So here we have 2 and 4 minus -1 and 3. So again, we can write it as 2 minus -1 and 4 minus 3. Or we can actually calculate that and evaluate it, which would be 3 and 1. Here, if we look at 3a, so again, we have our scalar multiplied by our vector. Here, we have 3 multiplied by our a, which is 2 and 4. So multiply the scalar into each of the components, both on x and y. So here we can write it either as 6 and 12, or write it as 6 and 1 and 2. Okay, here, example 3, or sorry, here with E, we have -2b. again, -2 multiplied by our b, which is -1 and 3. And here we can write it as 2 and -6. Okay, and then lastly, we have 2a minus 3b. So here we have 2 times the component of vector a, so 2 and 4, minus 3, and vector b, which is -1 and 3. Remember, the scalar needs to be distributed into each component. So the 2 into the 2 and 4, and the -3 into -1 and 3. Here, our result. So 2 times 2 will give you 4. 4 plus 3 will give us 7. And then 2 times 4 will give us 8. 8. 8 minus 9 will give us -1. So here, our component will be 7 and -1. Okay, so let's look at example 3. So example 3 says, again, if x is equal to 2i plus 3j and y is equal to -i plus 2j, determine vector x plus 2 vector y and the magnitude of x plus 2y. So here, again, we know that vector x is equal to 2i plus 3j, so 2i plus 3j plus 2 times, again, vector y, which is -i plus 2j. We'll distribute the 2 in. Here will have 2i plus 3j minus 2i plus 4j. Here we see that we can cancel out positive 2i and -2i. And so here we'll be left with 7j. Here, if we write it in component form, it'll be 0 and 7. So here, if we find the magnitude, again, square root a squared plus b squared. So here, the square root, here our a squared is 0, and our b squared is 7. So 0 squared plus 7 squared, which is equal to square root 49, which is equal to 7. Okay, and so here, again, we again determined the vector x plus vector 2y, and then we found the magnitude as well. Okay, and so continuing on, we're looking at algebraic vectors defined by 2 points. So again, here it says if a vector has an initial point of a, which we'll define as x1 and y1, and as a final point of b, x2, y2, then we want to find the, again, first, again, the vector ab. Okay, so the diagram is provided to us here on the right. So if you take a look at that. Okay, so here, again, we know that the A is going to be the tail, and our B is the head. Okay, so here, if we look at it, then we have O, B, and O to A. Here, again, we can write vector AB as, again, equal to vector OB minus vector OA. So here again, we have head minus tail. Again, it, so here's B minus A. Now here if we label, so here if we label our vector OA, that is equal to, again, x1, y1 in component form. And if we label our vector OB, then that would be x2, y2 in component form. Here, again, we see that our vector A to B, again, being A, and being B, and here will be equal to OB is, again, our x2 and OA, which is x1, and for our y values, y2 minus y1. So here, if we're looking at the magnitude of AB, then here we can write it as the square root, then a squared plus b squared is x2 minus x1, which is our a here, squared, plus y2 minus y1 squared, which is our b here. Okay, and then we're going to look at the unit vector of AB. And so how we calculate that is, again, we take the original vector AB and we divide it by the magnitude of AB. Here, and we can write that as 1 over square root x squared minus x1 squared plus y2 minus y1 squared times x2 minus x1 over y2 minus y1. And here you may have noticed, again, that our magnitude, again, is the same as the distance of the line segment formula. The magnitude of a vector is the same as the distance of a line segment formula. So example 4 says if, again, A is given 0.52 and B is 3,4, determine vector AB. So again, A here being the tail and B being the head here. Again, head minus tail, so 3 minus 5 and 4 minus 2, which is equal to -2 and 2. And here, the magnitude, again, will be the square root of a squared plus b squared. A here is -2 squared plus 2 squared. And that's equal to square root 8, which is equal to 2 square root 2. And then the unit vector in the direction of vector AB, that's equal, again, to the original vector over the magnitude 1 over 2 square root 2 times -2 and 2. Here we can rewrite our component as 1 over 2 square root 2, and we'll take out the 2 here, and as -1 and 1. And here the 2 cancel out. And so the unit vector in the direction AB is equal to 1 over square root 2, -1 and 1, or we can multiply that in, write it as a component form, which would be -1 over square root 2 and 1 over square root 2. Finally here, example number 5, it says given vector AB is equal to 5, 1 and A is equal to -1, 3, determine the coordinates of point B. So here we're going to let B equal x and y as our coordinates. Here, vector AB is equal to 5 and 1, and A is equal to -1 and 3. And again, we know that vector AB can be represented as vector OB minus vector OA. Here we see that we know that vector AB is 5 and 1. We don't know here our vector OB, so represented as x and y. That is our head, and minus our tail in this situation is our A, which is -1 and 3. Here we get that 5 and 1 is equal to x plus 1 and y minus 3. So here we see if we calculate it. So again, x plus 1 is equal to 5. Therefore, x is equal to 4. And y minus 3 is equal to 1. And therefore, y is equal to 4 as well. So therefore, coordinate B is 4 and 4.